the square root of x squared plus 25. And then x equals 5 tan theta.
That looks right to you?
Yes.
Okay, so we've got a number of things that you do in this. The first thing I'm going to do is change all these x's into something to do with theta. So I differentiate x with respect to theta, and that means I need to know what the derivative of tan theta is, which is 5 secant squared theta.
Mm-hmm.
And then we do a crossover, and that little bit is finished.
Okay.
So now I'm going to do x cubed, which is 5 tan theta cubed. Going to do the square root of 5 tan theta squared, because that's x squared, plus 25. And I'm going to replace the dx with 5 secant squared theta d theta. Are we okay with that?
Double check. Oop, I did square the bottom, so that's probably where I goofed. And okay.
Now, if you multiply this 3 times, I guess you get 125 tan cubed, because it's 5 tan theta 3 times. I'll just leave that right now because there's too much to do in my head, so that's still what it was. Now this becomes 25 tan squared plus 25.
Yep.
So far, so good?
Yes. I just did not square the tan theta on the bottom. So
that in itself might have been where it went wrong. Now these two guys become 625. You have a tan cubed theta. You have a secant squared theta. And I am going to simplify. I'll put it over here in some working. What this becomes. Right, this thing here. If you pull out 25 as a common factor, you get that. Do you know what tan squared theta plus 1 turns into?
I get 25 plus what? Sorry.
Tan 25 in brackets, tan squared theta plus 1. And my question is, do you know what tan squared theta plus 1 turns into?
Off the top of my head, no.
It is a standard one that you need to write down, so it's not in the top of your head, so you can just find it. It's secant squared.
Oh. Dang it.
And
I
so
should
what
have
you
guessed that one then.
Right, so what you get here is 5 secant theta. That's what this turns into. So the bottom turns into 5 secant theta d theta. So what I need to do now is cancel as much as I can, simplify. This secant cancels out one of them, but you still have a secant theta left. And this 5 cancels into that, not by much, but you do get something. You get 125. So it now ends up with 125 tan cubed theta secant theta d theta. So it started off life looking like that. We've changed it into thetas and it now looks like this. So now we have to figure out how to integrate this guy. This is a U sub. And when you do U subs involving secants and or tans, your U sub is a secant on its own or a tan on its own. You want to have a shot at what you think it might be in this question?
Gonna go with 125 tan cubed.
Right, we'd never use the number, and we'd never do
Oh, so
tan
just a
cubed.
10 cubed. Oh,
We
10.
wouldn't ever do tan cubed. You would only do a tan on its own or a secant on its own.
Oh,
Anything else you do is not going to end well, so don't do it. Secant on its own, secant theta or tan theta? What do you think it might be?
secant.
That is correct. Now I'm going to do a u sub of secant theta. That makes du by d theta secant tan, which means when we do the crossover, you get that, and then you isolate the d theta. So what we now have is 125 tan cubed theta secant theta, and replacing the d theta with this stuff, you get 1 over secant theta tan theta du. And whenever you do secants and tans, don't turn them into u's too early. Do this instead. Now that secant cancels out all of those, and that tangent cancels out one of them, and you're left with tan squared. So I now have 125 tan squared theta du. That's pretty typical. So what you then have to do is figure out how you're going to replace this tan squared in terms of secants and secant squares probably. That way you can get it turned into u's. So do you know what tan squared looks like in terms of secant squared? And you need that list somewhere handy.
Would it just be 1 minus secant squared then?
Oh, excuse me. Almost. Just go the other way.
Yeah, that's funny. If I just did that backwards, so secant squared minus 1.
Right. And that makes the thing become 125 u squared minus 1. Which becomes 125 u squared. Take away 125. Now we can power roll that guy. And we can do that guy. And then turn back into, in this case, secant thetas. So you would think, oh, well, God, thank goodness we're over, but we're actually not over yet. That's what makes these questions like take forever and a day, because haven't we to return our answers back into X's? And that's where you kind of put a little wall for a few moments and you go and return back to here. Because x over 5 then is tan theta. And the tangent is opposite over adjacent. And this allows me to construct a very special triangle. This triangle allows us to turn this or anything into x's. So theta is opposite adjacent hypotenuse. And the tangent is opposite, so x adjacent is 5. And Pythagoras, the third side, you get it from these two guys, and you get x squared plus this guy squared. And it's the square root of them, which is exactly this guy. So that's a good sign. So what I now do is I go looking for, in this case, secant theta. Well, let's see, what would secant theta be? Well, it's the same thing as 1 over a cosine. And I know what a cosine is. A cosine is an adjacent over a hypotenuse. which is 5 over the square root of x squared plus 25, right? Opposite over adjacent. Sorry, adjacent, sorry, over hypotenuse. Now the secant is the reciprocal of that. So you just turn this thing upside down. And that's what the secant is. So our answer is 125 secant squared, cubed, I should say. Take away 125 secants. We can tidy that up. You get this guy cubed over 5 cubed. 5 cubes 125, so it cancels out that guy. Bottom line is you just get a third. Oh, and this guy cancels with this guy, so bottom line is you get 25 of them. And 2 pages of work to find just one answer. Which is why you only got 7 questions, because they took forever and a day to do. I'll leave it there for a second, and then we'll have to move on.
Appreciate it.
Not a problem. Right, you got this copied? Can I move it? Right. Then if I keep this video on so that people who watch this can see that question in more detail. So okay, if I do that? Thank you. I'll just move this over. Oh, where shall I move it? So I'll move this down here. Right, how are you today, Catherine?
I'm hanging in there. How are you?
I'm doing okay. Matt, how are you?
Hanging in there.
Yeah, I know how that works. Katie, you look a bit tired. Are you tired?
When am I not tired?
I didn't quite catch that. What did you say?
I'm always tired.
Oh, you were born tired, right? So when you were born, the first thing you did is go to sleep, right? Just getting myself set up here. Okay, I think that's going to be it. Well, good evening, everyone. We seem to have a small group today. I'm not quite sure what the problem is, but nonetheless, we need to get started. We are going to be finishing off today section 7.4, and then we'll talk about the other sections after that. Last time we left off, we looked at how to find the integral of a fraction, and we used a technique called partial fractions. In fact, there was 2 techniques, wasn't there? One of them was called partial fractions, and the other one was called the general algebraic method. And the partial fraction method was a bit of a magic, right? You did it and it worked, and that was fine. But today we're going to look at what's called the general algebraic method. Now you can use this method in any situation that you're likely to see in 7.4, right? So you can use it when the bottom terms are linear, but you have to use it when there's anything that is squared. So you must use it when you have a fraction and on the bottom of that fraction, there is something squared, right? So let's see what that might look like. There are two main versions of what that looks like. They're a square because there's an x squared plus 9 there. Actually, let's make this a little bit more interesting. There we go. That's one situation. And the other situation is that the terms are linear, right? They're x's and x plus 7s and whatever it is, but there is one of them that's got an x minus 1 all squared. So those are the two situations that we're going to deal with and do this. If you said something, Taylor, I did not catch a word of it.
Sorry, I didn't mean to. I thought I was muted.
Okay. Then are we good so far? Right. So, general algebraic method, new technique. Going to use it when there's a square, like x squared plus 9, or when there's a square here. And I'm going to show an example of each one of these two, and they'll be the template for every other question that looks like these. Okay. Doesn't really matter to me. Do you want to do the top one first or the bottom one first? We're going to do both anyway. Anybody got a preference? Yeah, we'll do top one then. Oh, perfect. That's the one I was going to choose. For no particular reason except it's on the top. So there's a kind of shopping list. Like, buy this first, buy this second, right? So it's do this first, do this second, do this third. The first stage that you're going to do here is that you're going to take this fella and you're going to split him into his partial fractions. And there's only two of them. That's good news. But can anybody remember what goes above the x squared plus 9? What letters and things go above x squared plus 9? Last chance. Above the x squared plus whatever the number is, in this case plus 9, you always do two terms, something x plus a number, right? So in this case, bx plus c. Now, I'm going to write down a lot more lines than you typically would need to write down. And what I'm going to do now is I'm going to focus on just this bit and forget about the integrals and the dx's until later. So we already know it's going to be this guy plus this guy. Well, what you do in the general algebraic method is that once you've split them into their partial fractions, which is what we call these, you then figure out how to put them back together as a single fraction that shares this term here as their common factor. Well, this fraction here, I guess I could do it in red, you would multiply it by a special version of 1 called x squared plus 9. And this fraction here, you would multiply it by a special version of 1, x minus 2. Now, those aren't just random pulled out at the top of my head. Can you see that if you want them to share a common denominator, in particular this common denominator, then you need this to have an x squared plus 9. If you multiply a fraction by 1, you don't change its value, you only change how it looks. So that's why this works. This guy's already got an x squared plus 9. What he's missing is the x minus 2's. Now you put these together, and now you have ax squared plus 9 plus bx plus c x minus 2 all over these two guys. And that's this fella. So, quick recap. You take the original and you break it into its two partial fractions, these fellas. You then put these two fractions back together again by multiplying by some special versions of one, and now you're looking at that. So superficially, you might say that was a lot of work to do nothing, because we're no closer to getting the values of A, B, and C than we were when we wrote them up here. But you have to bear with me. Since these fractions are equal and they have the same common denominator, that means that 10x plus 2 is going to equal a x squared plus 9 plus bx add c x minus 2's. In other words, the two top things must also be equal. And now I don't have any fractions to worry about. What I have in mathematics is a general expression involving x's, numbers, and a, b's, and c's. And although it might not look it, this is actually true, this expression, for every single value of x in the universe. So if you plugged x equal 1 in here, it would be true. If you plugged x equals minus 50, it would also be true. And we're going to use that fact to get A, B, and C. So the way the general algebraic method works is you now choose values of x. And you don't just choose any old number, because that wouldn't help. Look at this expression over here. I want to choose a value of x that basically makes everything disappear, right? Except one of the letters, A, B, or C. So I'm going to choose just one value of x that makes all the other letters disappear, right? Turn it into nothing, so whatever you want to call it, disappear, and only leave one of the letters behind. Can anybody see a good choice of x that would do that job?
2.
And the reason you picked that, which is the right answer, I'm assuming, is because won't this be 0? And won't 0 times this basically make all of this disappear? So what do we get? Well, if you make x 2, you get 10 times 2 plus 2, you get 22. And you get a, and you get 2 squared plus 9, which is what, 13, plus some stuff times 0, which is just 0. And that gives me one of my answers. I now know who A is. Now, if I was the person who did WebAssign, do you know that A would be 26 over 13 and would come out as a nice number like 2? But since I'm not that good at designing questions with nice answers, you're going to have to live with some ugly answers. But I have seen some of the answers to the WebAssign questions, and not all of them are nice numbers either, right? Some of them are 17, 15s and weird stuff like that. So that's not that, pardon me, unusual. So what do we do now that we know one? Return back to this equation here. Replace the A, because we now know what it's worth, by 22 13s. And so I have 10 add 2 is 22 13s, x squared plus 9, plus bx plus c, x minus 2, right? So this has now become that. And repeat the process. Look at this expression here. There's a B and a C still to be found. Great, right? Still to get a B, still to get a C. Pick a value of X that makes one of these guys disappear and the other one survive, right? So I can't pick X equals 2 because they all disappear, right? That's not any use to me. So I have to pick a different X. What X you think might be useful to kill off one of these and leave the other one alone? What value of X would be a good choice?
Zero.
Agreed. Do you see why 0 is a good idea? Isn't that going to just disappear because B times 0 is 0 and it's gone? So let's see what we get then. We get 10 lots of 0 plus 2, which is 2. We get 22 thirteenths, 0 squared plus 9. We get B times 0 plus C, and we get 0 take away 2. So we have 2. Oh, yeah. That's not my best choice, but here goes. 22 times 9. We get 198 thirteenths and negative 2C. So we take this guy and this guy, and basically you subtract it from both sides, which is what calculators are for, because I'm not even going to try that one. 2 take away 198 thirteenths, and then just do the math button choice 1. And the answer I get is negative 172 thirteenths. And then divide everybody by negative 2. So I can actually do that in my head, because 172 divided by 2 is 86, and I get positive 86 thirteenths. And now I know C. So we've figured out A. We replaced it in here to get this expression. We chose X equals 0, and now we figured out C. So I'm going to go here and rewrite the information, but changing the C into 86 thirteenths. So I have 22 thirteenths, X squared plus 9, plus BX add C, X minus 2s. So basically I'm taking this line and only changing one thing. I'm changing that C into 86 thirteenths. And we're almost done, because we choose one more X. Now you might think, what X will I pick this time? Well, your decision's a little bit different and a lot easier. Since there's only one variable left, I don't need to pick an X that destroys anybody, right? I got one letter, right? There's only one letter left. All I need to do is pick any X I like that I haven't chosen before. So I've chosen 2 and I've chosen 0. So any X would work. So Katie might pick 42 because she's feeling bored and she wants to do a big long question. And Catherine, on the other hand, wants to get this damn thing over with. So what X are you going to pick, Catherine? Since anything works, what are you going to pick?
Ooh, let me see here. I'll go with X minus 2.
Oh, just choose one X. Choose a value for X, one number for X.
Oh, just a number. Okay. Let's go with 6.
You're not very helpful. Will 6 work? Yes, it will. And it will probably be just as ugly as mine. But I'm going to pick 1.
Okay.
Why do you think I'm picking 1?
Was it simpler?
Because it's simpler. That's the only reason I'm picking it. Would 6 work? For sure it would. Based on the fact that this is already ugly, I don't think 6 would be that much a problem. I think it would be ugly, but so's X equals 1. Now, since I know X equals 1, 10 lots of 1 plus 2 gets me 12. 22 13ths, 1 squared plus 9 gets me 10. Oh, it's nice because bx just becomes into b, plus 86 13ths, and plug in 1 here, you get -1. So that's what this expression looks like when you replace all the x's with 1s. And what I'm going to do is I'm going to solve for b. Well, here goes. 220 13ths minus b minus 86 13ths. 86 away from that. So 220 take away 86 leaves me with 134 13ths minus b. If I subtract that fraction from both sides, so here we go, 12 take away 134 13ths, I get 22 13ths. And that makes b -22 13ths. And we can say, thank goodness for that, we have finished finding out who A, B, and C is. We now know who this guy, and this guy is. So let's continue then. I now know that my original question, which was this fella, can be written as the integral of A, which is 22 over x minus 2, plus bx, which is -22 13ths x, plus c, plus 86 13ths, all over x squared plus 9 dx. Right, so give brain a little pause here. This method, called the general algebraic method, is extremely long. You agree? Can you understand why we love the cover-up method when it's linear? Why we choose to go that route? Now, we've went this route because it's the only route that's open to us. That means we have to integrate these things. So let me show you how that works. There's still a little bit of work to do. Separate out these guys into 3 distinct integrals. Now, the next line, although you don't need to do it, I'm going to do it because it makes my life easier. I'm going to pull those ugly fractions outside the integral sign, which is allowed to, well, that's actually a plus there. So this is -22 13ths goes here. And the advantage of pulling out these ugly fractions is that it makes the integral that you're going to deal with a lot easier without getting distracted by these 22 13ths and things all over the place. Now, each one of them gets integrated and we're finished. So let's see what that might look like. Would you agree that 1 over x minus 2 is just a natural log of x minus 2? You happy with that one? So when I integrate this, I get 22 13ths, the natural log of x minus 2. Can you remember the x squared plus 9 was a special version of the inverse tan? And what you get is 1/3 the inverse tan of x over 3. But if that was x squared plus 4, it would be 1/2 inverse tan of x over 2. Okay, what about this fella? X over x squared plus 9. I need to find the integral of x over x squared plus 9. And this is something you might not have expected, but darn it, you're going to have to live with it. What would I need to do to find that simple integral? It's not that simple fraction, I should say. Do you recognize questions? Yeah. So after all that hard work, you still have a U sub to do on one of the pieces. And would you agree that x squared plus 9 is the right U sub? So let's see what that looks like. You get 2x. Do the crossover and isolate the dx. So I'm doing this kind of working outside. So it's going to be x over u times 1 over 2x du. And I'm going to write that as 1/2 1 over u, because x is cancelled. And that's 1/2 of the log of u. And that's 1/2 of the log of x squared plus 9. So this fella here is negative 22/13 of 1/2 of that guy. Well, let's see what we got. We got 22/13 this fella. This guy, when you combine them, gets you 11/13 because the 2 and the 22 cancel partially. And this guy, I don't think they play well together, do they? No, they don't. So you finish with 86 over 39 inverse tan x over 3, I'd say. If you look at kind of the whole big picture thing, it's kind of scary. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2 to 3 to 4 to 5, 26 lines of working at least to get that final answer.
Yikes.
That's a lot of working, but we did get the answer. So if you want to, if you want to do partial fractions, you want to do linear, don't you? You want to do the cover-up method. There is no argument. You do. So that one question is the only example I'm giving you of this, but I believe you've only got one, if more, at most 2 in the homework. So it's not like you got a lot of practice there either. So I'm now going to look at the second situation. Again, we need to use the general algebraic method on this one. Now, when you have an x minus 2 squared, as you do here, it's a linear term being squared. The split is a bit different. You get a over x minus 1, which most people might pick. And then you have a b over x minus 1 squared, which more people would pick. And then you'd have a c over x plus 7 that I think everybody would pick. But do you notice that there's 3 terms, not 2? And in particular, have you noticed that the x minus 1 squared generates 2 distinctly different fractions? And that's important to do this process. So what I'm now going to do is focus on finding A, B, and C again. And the good news, if we can have any kind of good news, is it's the same process. So here are my 2 fractions written out again. And I want to put them back together again, sharing this common denominator. So if I look at the x plus 7 one, do you see that he is missing an x minus 1 squared? So that's the special version of 1 he gets. The term in the middle has already got an x minus 1 squared. All he's missing is an x plus 7. So that's the version of 1 he gets. What does this fella get? Because he's the weirdest one of the three. How do I convert this to share this common denominator?
X minus 1 times x plus 7.
Correct. Now, if you do that, you get this fella on the left. And again, I'm putting in more lines than you need. Hopefully you'll look at this and you'll say, I don't need line 4 or line 6. That's great if you can do that. So we now end up with this fella. And then we say, look, the bottoms are the same. That makes the tops, the numerators, the same. Now that's pretty much the same 4 lines that we did in the other question, isn't it? It's the general algebraic method. Break them apart into their partial fractions, figure out how to put them back together, just here, and then make the bottoms disappear and focus on the top. Have you a guess what I'm going to do next? Based on what we did in the previous question, what do you think I'm going to start doing next?
Find a, b, and c by choosing a value for x.
Correct. And this is not random. You can only pick certain x's, and you must pick them in the right order. And isn't the goal to choose an x that makes everything else disappear and just leaves behind one of the letters? And it doesn't matter which one is left behind, just as long as it's one of them. But saying that, you have to be careful, right, about which x you pick. Because you can't just say, oh, I'll pick 0 and see what happens, or I'll pick 4 and see what happens. You'll be here all day if you did that, right? There's a logic to who you should choose. Now, looking at this expression here, would you agree that x equals 1 and x equals -7 are very good candidates for the guy we should pick? And why would I choose those? Well, don't they make things become zeros? Okay, so what value of x should I pick? Who should I choose?
1.
I like 1. Now, if I choose 1, won't that be 0, so they'll disappear? And won't that be 0, won't this disappear? You notice that choosing x equals 1, only the middle term actually survives. So let's see what we get. 3 lots of 0 plus 1 is 1. If you plug in 1 in here, you basically just get a times 0, so you get 0. If you plug 1 in here, you get b times 8. And if you plug 1 in here, you just basically get 0. So we now know b.
Should the first term equal 4?
Did you catch that deliberate mistake? Because I'm glad you did, because I didn't. Actually, I kind of like that, because isn't a half a much nicer number? Fraction. Okay, we now know b. So we go back here and we write down exactly the same thing with one change. B gets replaced by a half. And now you choose your next x. Now you can't choose 1. That's you'll never choose the same guy twice. Trust me, it doesn't go anywhere. So I want a new value of x, something that's going to make everybody disappear except one piece. So who do you think we should go for this time?
-7.
I agree. Would you agree that -7 is a good choice, and why is it a good choice is the thing that should be crossing your mind. So I'll try and do this one correctly. 3 sevens is -21, add 1 is -20. Not a bad number. Won't this be 0? So the whole thing is 0. This will be 0, so the whole thing is 0. And this will be c times -8. So I have -20 is -8c. Dividing both sides, and oh, do a 4 on them, that's 5 halves, I believe. Hey, actually, it's quite a nice answer. Great. Compared to the other one, 5 halves is almost nice. And now that I know this fella, don't you return to this one and write everything down except change the c into 5 halves. And okay, we've chosen 1 and it did a good job. It allowed us to find out what b is. We chose -7, it did a good job. It allowed us to find out what c is. There's only one guy missing now, right? A. And we have to choose an x. Don't pick 1. Don't put -7. Now, last time I told you, Catherine, you said 6, didn't you?
Yeah, that's what I said, 6.
Right. Now, 6 would work, but I'm not picking it. You can pick it and it'll work. Think lazy. Think easy. Think
Just
the
go with
simplest x. Well, you could do 1, except we've used it. I probably might have used it. So pick even simpler than 1. What's the
Zero.
easiest number? I hear
0.
0, right? 0. You agree that's the easiest one to work with? Could I have chosen 6? Of course. That's the amazing thing. You might not think it looking at this mess, that every time I pick an x, I'm going to end up with a different value of a. But the truth is, no matter what value of x you pick, you're all going to end up with the same a, which is kind of nice. So 3 lots of 0 plus 1 gets me 1. A minus 1, 7, plus a half of 0 plus 7, plus 5/2, 0 take away 1. So what have we got?
Isn't
We've got-
x minus 1 supposed to be squared? Cx minus 1.
Oh, good. It had no effect.
No, the second one.
Oh, the where?
C.
X minus 1 here
C.
is not squared. This one should be squared. Yes. So where did I lose it? I forgot to do it here when I
The
did my
C will be
transfer.
different.
Okay, so we're going to have to, sorry about that. This is squared, so what do we get? -20 equals 64c, because that's what you get there. Divide both sides. We get that. That's going to go with a 4, isn't it? So what you're going to get 5/16. Not as pretty. So as if the last few minutes didn't happen, I'm now rewriting this equation with the correct value of c. So we have this fella plus this fella. It's technically -5/16. This guy. And I'm still going to choose 0. So that fella gets you 1. That fella's going to get you -1. That fella's going to get you 7. That fella's going to get you 7. And that guy there's going to get you -1, but when you square it, you get 1. So you're still going to end up with that. So negative 7a plus 7 halves, take away 5/16. Oh, darn it in space. Let's see what that ends up being. Let's join these two. 7 halves, subtract 5/16. And the answer you get is 51/16. Subtract it from both sides. One, take away 51/16. That gets me negative 35/16, which gives me a of 35/16. I hope I didn't screw up anywhere there, which, if I am correct, then the original question was this fella. And it ends up being A, which is 35 over x minus 1. Then you have a B, which is a half of x minus 1 squared. And then you had a C, which is negative 5/16 x plus 7. And I'm going to separate them out as 35. It's not 35. Where the heck did I get 35 from? What's A? 35/16. There we go. So it's 35/16 x minus 1. A half 1 over x minus 1 squared. Take away 5/16 x add 7. And then for each one of these guys, we find their integral. This fella is just a natural log. This fella is also a natural log. We got one awkward guy in the middle. Any ideas how I'm going to do that fella? Because there's really two different ways both work.
U sub.
Okay. If you do the U sub, it's going to be x minus 1. And that works. I'm going to show you a different way. Again, I could do the U sub, and that would work. Only I'm going to do the linear shortcut method, which says add 1 to the power and divide by the new power, which basically just gives me that guy. So you can do a U sub and you'll get this as an answer. You can do a U sub to this guy and this is the answer. Or you can use the linear shortcut method and get this answer. And remember, there's a half here, so negative a half over x minus 1. And you're finished. For completeness sake, if you did the U sub, you'd get this. So this fella would turn into 1 over u squared du, which would become u to the negative 2 du, which would end up being this guy, which would be that guy. So that's why it works. Right, a lot to take in there. Any questions about that particular process? It's called the general algebraic method. You ever saw those horror movies where you're close to the end, but you know there's still 15 minutes to go? Yeah, everything looks like, you know, the monster's been killed, everybody's safe, and so on. And then just when you think everything's safe, doesn't the monster come back and attack somebody, and there's a big fight at the end, and so on, right? So you might think, I am so glad that these questions are over. The monster is dead. I got the answer. And for those questions, actually, it is dead. But there is an extra twist, like you very often get in some of the really bad horror movies, when you find out that the real hero is actually the murderer. You know those kind of stories where you go, oh, come on, that's not right. Well, we are going to look at some questions. Essentially, we're going to be looking at questions 10 and 11, where they ask for one more level of complexity. What does that mean? Well, as if the question wasn't bad enough, you're going to get a question where you have to start by doing substitution before you even do the partial fraction method. So if you just hold on with me for a few minutes, I get timed out, so I'm going to have to go back in, and I'm going to show you what those homework questions look like. Did you hear about the high school students who get caught in the car park of their high school at night by the police? And one of them was drinking battery acid, and the other one was snorting gunpowder. Do you not hear about those? Well, do you know what happened to them?
They died?
One of them was charged and the other was let off. Oh, come on. That at least deserves a groan. Right. What do you mean I'm currently not listed for any course? Excuse me. WebAssign is fighting with me to tell me I'm not registered, which is kind of strange because I'm the one that's running the class, so you know why I'm not registered. Okay, finally got the darn thing. Almost, you know, hold on, we're almost there. Have you ever done that when you do your homework, that you go back and you find it's timed you out? Is that not annoying? Yeah, I think so. Well, if it makes you feel any better, I get timed out as well. So it's not been picking just on you. Okay, so let's have a look at those questions. I'll switch over. And what are you doing? Oops, don't want that. Okay, spoke too soon. We've got one more thing to do. It was showing the solutions, and I don't want to see solutions. Right, finally got the thing up and running. Oh, sugar and spice. Where are you? Stop sharing. There we go. And begin to regret actually doing this, but we need to do it because you need to see what they look like. And you need to see how they're phrased so you know when it's happening. These two questions talk about making a substitution Now, when you see the word making a substitution, will you just say make a u sub, because that's what they mean. And in each one of these two examples, we have a u sub to make first. Once we've done the u sub, the integral will turn into a partial fraction question, or at least something that we should be able to get the answer to. So there are two of them. The first one is dx, x over the square root of x minus 1. And the second one is e to the x over e to the x take away 2 and e to the 2x plus 1. Okay. Now, let's return and figure out how that's going to work, how we're going to make it, how we're going to solve the question. Right, I don't know how many windows I've got on, but far too blinking many. Here we go. I'm going to pick this one first because I want to. They tell me it's a u sub, it has to be a u sub. I need a u sub. But it's not a normal kind of obvious u sub. But nonetheless, it must be doable. Any gut feelings for what the u sub in question 11 is going to be? And you have to think outside the box a little bit. I don't mind. I mean, just, you know.
You do 2x?
E to the 2x, is that what you said?
Yeah, but I don't know if it works.
Yeah, you're right, hesitating, but you're dead close to the one I'm going to use. Just shrink it down a little bit, not e to the 2x.
2x.
Too much shrinking. Halfway between those two.
Would it be e to the x?
Yes, e to the x. So you were in the right ballpark when you said e to the 2x. But you're kind of also right. Did you notice that e to the 2x wasn't going to play well with these two guys? Which is why that would have been a bad choice. But you you got that feeling that wasn't going to be perfect. Now you might think, well, e to the x has got problems, and it does, but we can fix those ones. If you differentiate it, you get e to the x. You do your crossover, and you get the place where you isolate the dx. Well, let's see what we get. I'm going to just write everything down. Without changing anything. This is probably an extra line that you might not feel you need, but I'm going to do it. Now, do you notice that, so there is some good news. Don't the e to the x on the top cancel with this one? And now I'm left with this fella. Which superficially looks like we're in deep doo-doos, but we're not. Don't I need to turn these terms into u's? Now, e to the x take away 2 is a pretty easy one, isn't it? It's just u take away 2. Now, the sneakier one or the harder one is how am I going to write e to the 2x using u? It's not too bad, actually. What do you think e to the 2x would be in terms of u? Any ideas? E to the 2x. Suppose I told you, well, go the other way. Suppose I told you that e to the 2x was the same thing as e to the power of x squared. Then wouldn't e to the 2x Just be u squared. Do you recognize that ugly fraction as a partial fraction question that you would need to do the general algebraic method on? And 20 minutes from now, we'd have the answer. But that's your job. Do you recognize it? Partial fraction question. So that's how you're going to tackle that one. Now, the other one, question 10. And the only difference I'm doing is I'm writing it like that. I just don't like dx's in the top. I like to have the thing separate. And we're told it's a substitution. So we need to figure out who the substitution is going to be. And there are a number of possibilities. And very often what you do in a really difficult question is that you try something, and if it works, great, right? You're done, finished. And if it doesn't work, then you try something else. And then if that doesn't work, you try something else. Now, in a question like this, there's really not that many choices. Would you agree for the use of? Right? What would you think might be your first option as a use of?
X minus 1.
Totally sensible. And 9 times out of 10, it will work. But this is 1 in 10. So you plug it in and you do some stuff, and then you go, oh God, it's worse looking than it was 5 minutes ago. That wasn't a good idea. But you don't know until you've tried. So can we pretend we've tried and it didn't work? But it was a very sensible use of. It's one I would have picked in many other circumstances, just not this one. So now we're in the, what on earth can I use? Because there's not a lot left. Well, you know, like Sherlock Holmes went and said, once all the other things are eliminated, whatever's left must be the truth. What's the only thing I haven't done as a use of, apart from X, which is pointless? Who's the only other use of left?
1 over X.
Okay, that one was the one I never thought of. So you try it and it fails on you. But you're right, that was one I didn't think about. It's almost like you're trying to avoid the right one. So whatever you were trying to avoid, actually say that one first.
It's not 1, is it?
No, I wish that would have been a great one. I don't want to write this one down, because if I write it down, the next time you see this question, you're just going to say, I didn't know how you picked the first time, so I'm not going to be able to figure out how you pick it another time. So
I feel like I'm gonna feel dumb once I see the answer.
Yeah. So we gotta, you know, I'm going to fight like heck not to tell you yet. Well, let's look at
Whole
it.
thing.
Whole thing. Could work, didn't. Never seen the whole thing ever work, but that doesn't mean there's not going to be a question in the universe where that is the right one, but I doubt it. Okay. So can't use 1 over X, can't use X, can't use X minus 1. Not one of you have went near the most obvious thing in this expression. What's the most obvious thing in this expression that you haven't even mentioned?
It couldn't be the square root of X minus 1?
It could be. Is your brain fighting that? Because that's the one that works. Now, I can imagine why you don't want that. You're thinking, this is going to be ugly when you differentiate it, and this is going to be this, and this is going to be that, and I agree, but nonetheless, I'm going to use it, and if it doesn't work, I'm going to look kind of silly, but that's fine. I've looked silly before in my life. I'm going to call it X minus 1 to the power of half, because I need to differentiate, right? And square roots are called half powers. So when you differentiate with respect to X, you get 1/2 X minus 1 to the negative a half. Are you happy with that? Technically, it's a chain rule, but times 1 doesn't do anything, so I'm not worried. Are we good? Okay. Now, crossover. Well, I'm not actually going to do the crossover yet because nobody, well, I don't like that. Are you happy with that becoming this? Can you see what I did? Isn't that a half power in the bottom, which is the square root, and isn't 2 in the bottom? You know, half a 2 in the bottom. Right, now I'll do the crossover. Oh, hey, I managed to isolate the dx here, right? So let's see what we get. We get an integral of 1 over x, the square root of x minus 1, times 2 lots of the square root of x minus 1 du. And those square roots are gone. And we are now looking at that. Agreed? Now, we don't want x's. Don't we want that x to turn into something we use in it? So I'll return back to this fella. Shouldn't we be able to do some algebra on this and solve for x? Agreed? So what would I do to both sides to get closer to finding x?
Square them.
Yeah. Then good. Now, what should I do next? Add 1. So this fella becomes, and then you say, thank you very much, because this question doesn't even need partial fractions. Isn't this just 2 inverse tans? And of course, return back to the x's. That is actually question 10. There is no variation in that one. So I've kind of done one of your homework questions for you. And that is the end of partial fractions. Are we good? Any questions about those two? Or can we close the book on that section for now? Don't see anything, so I shall move on. Now I'm going to have to do the usual, figure out where the next section is, and here it is over here. Okay. So, technically who is next? That's kind of what's the next section we should do. Well, it's not as clear cut as you think, so let me show you what's going on. And that's not the right one, I don't think. Try that again. Oh, it was the right one. Let's click on this section here. Right. Do you see, I hope at least, do you see my version of what WebAssign looks like? And there's partial fractions here. So the next section says strategies, optional. And strategies and integration, if you want its full title, but I didn't have enough room for that one. So I put this one as optional, which means it's worth 0 points. So if you do the homework for this, you can't lose any points. What's inside it? Well, let's show you. I may have to move it over here. I think I need 3 screens. My wife's not going to fall for that. I've already got 2 screens. And if I say, I think I need 3 screens, I can imagine her answer. What does anybody need 3 screens for? If you've seen the amount of windows I have to move around and complain about, and I'm not surprised that you're not fed up with me complaining, you would probably want 3 windows as well. Right. So I don't know, are you looking at the inside of 7.5 now? I've opened and closed so many windows, I'm not sure what I've done. Right, there are a whole 21 questions, so it's totally optional. So you might just go in and do some, you might go in and do them all. What you have here is essentially integrations where you have to pick the method. So let's think of what the methods are. Power rule, what I'll call them standard integrals, right? A standard integral are the ones you just know the answer to, right? 5e to the x is 5e to the x, right? That's one. U subs, they're big, right? Trig substitution, x subs, integration by parts, and partial fractions, right? So about 5 strategies. If you were doing question 1, what technique would you use to do question 1? Make it a bit bigger. Because imagine your final's coming, which it is, and you get this question. What method are you going to use to solve question 1?
My first thought is trig substitution.
Oh, what would your substitution be? Because that isn't a bad idea.
I was thinking cosine squared, but I don't know if that's.
Oh, no. Yeah, I see where you're going now. No, but the trig's good. How about a u sub? 6 minus sine x.
Yeah, that makes more sense.
That would work. Try and think simple before you think hard, right? That's what I try and do, because sometimes you see something. What would 2 be? Question 2. What technique would question 2 be? It's got a particular shape to it that's a bit of a clue. It's got a log in it, which is also a bit of a clue.
Is integration by parts?
Correct. And you'd make the f of y, in this case, it's variable is y. F of y would be log y, and the g of y would be y to the half. And trust me, it works, right? It works. If you're doing 3, it would be a u sub. What would the u sub be in question 3? Think simple before you go hard.
Would it be cosine?
It would be. Okay, you're going to be left with a sine squared, but that turns into 1 minus cos squared, and that becomes 1 minus u squared. So it does work. Well, they just keep going on and on. There's one. There's a trig one, so it's a u sub. Sine x or cosine x. What would you use in question 7 as your u sub?
Cosine?
Yes. Lucky guess, or was there a reason?
I see that sine is to the power 5, so I want to reduce that.
Yep. So pick the even one. Does that? Yep. So just pick cosine. Have you noticed that you only pick sine or cosine on its own? You never pick, can't say never. 99% of the time, you don't pick sine cubed as your u sub, right? You just pick sine. Like 99% of the time, don't you only pick tan x as your u sub, not tan cubed x, right? So think small, right? U subs, think simple rather than big ugly things. And that one's an integration by parts. This one here, oh, do you recognize question 9? This is the first time we had a question you needed this technique. It should be scary in your brain.
That's the x sub, right?
Yeah, that is that downright ugly x sub. You might or might not recognize this one as x equals sine theta, but you could always find out which one of the three you use. So you see how this thing is working. Question 11 is a baby question. What's the integral of question 11? And I call it a baby question for a good reason. It's hardly grown up yet. 5e to the 6, antiderivative.
Would it be 5/7 e to the 7th?
No, but I know why you thought that.
Be 5e to the 6 plus c.
Almost.
5e to the 6x plus c.
Correct. Isn't 5e to the 6 just a weird number? And when you integrate a number, don't you stick an x at the end? So it's just a power rule. Just 42 gets you 42x. 5e to the power of 42 sine 15 still gets you what I just said with an x added at the end. Ooh, that's a cool one. I'm not even going to go near that one. What would 14 be? Well, let me tell you what it would be. 14 would be a u sub. Which u sub would you use in 14?
1 plus square root x.
Like it. Yeah. That would work perfectly. That's probably the one I would pick. And as a backup plan, you could have done just square root of x, and that would have worked. I think it would be much uglier, but it would have eventually worked. So sometimes you can get lucky and two different u subs will get you out of trouble. 16. It's a secant or a tan. Agreed? It's a u sub secant theta, or it's a u sub tan theta. Who is it?
Tangent.
I like it. If you pick tangent, can you trust me? You just get u to the 7 du. Do you know if you pick secant, technically it would work, but it would take you 3 times as long. So, you know, it's not the end of the world if you chose the wrong one in that case, but it would be a lot more time and effort. 17 is a trick question. The buggers, that is a trick question. They are not nice. Can you see anything in 17 that makes me say, ooh, that was dirty?
Would you do trig substitutes?
Well, you might later on, but before that, there's something you can fix. Look closely at 17. What the heck is going on here that you might be able to work with before you even think about integrating?
Did you factor out a secant theta?
The darn bugger's putting a secant there. That turns into 8 tan over 1 minus secant. Now, it might not look like good news, but if you did some trig identities, that actually comes out quite good. Think outside the box. Well, maybe not too far outside the box. What would the u sub in 18 be?
I want to say 16 plus e to the x.
Go for it. That's the one that works. Right. That's the one that works. What do you think it's going to be in 19? So u sub. Any thoughts on the u sub in 19?
X plus c.
X plus
Yeah, x plus c. It's really messy math, trust me. You do not want to do that question. But since it's optional, you probably shouldn't. You might say to yourself, I would use a u sub of x plus c, but I do not want to spend 20 minutes finishing the question. And that's fine. You probably wouldn't get one as ugly as that in the final because it would take too long. But that would be the u sub. What about, oh, that's a cool one. Definitely think weird on this one. What do you think the u sub is going to be in 20?
E to the square root of x.
Do you know, I didn't think about that, but I think that works. I think that works. I'm not going to do it, but I got a feeling that could work. It's a really weird derivative, but I think it would work. Do you know who I was going to pick? Which I do know will work.
Just the square root of x?
Yeah. But I think you might want to check it out, but I think e to the square root of x would probably have worked and be easier to do as well. So my choice would have been the longer of the two. If you get 21, then you should just go home tonight because there is nothing anybody's going to put out in front of you that is harder. What on earth are you going to use as your u sub in 21? Because it really isn't even vaguely obvious. And it breaks about every rule I've told you not to break. I'm only going to give this one a 30-second because I'm not surprised you wouldn't have got it. But put it out there, just chuck something out, and maybe you will get it. Ryan, you got a thought?
I was gonna say cosine, but then I saw that it was sine 2x, so I
Okay, but you're darn close to picking the right one.
Would it be cosine squared?
Yes. Now you might not. Why did you pick that? So it's bang on. What made you think cos squared? Not cos 4, but cos squared, which is the right choice.
Because then you can get the derivative to cancel.
Right, and the derivative ends up being a version of 2 sine x cosine x, which is what sine of 2x is. So that'll turn into, I think, negative 10 over 1 plus u squared, which is an inverse tan. That is not a finals quality question. I like to put a bonus question in final exams. So that's the kind of question I would pick as a bonus, which means you get an extra 5%, if 5 points anyway, not 5%, if you got it right. But even if you didn't get it right, you can still do perfect. So that's what that section was about. Now, we didn't do any of them, and it's up to you how many or how few or any that you choose to do, because it is optional. And that's good. That's what it is. And that's the end of that particular section. So are we still looking now at the screen? Does it say section 7.5? Okay. Now 7.6 is integration using tables, and that's not there. 7.7 we did in week 1. Remember Simpson's rule? Chapter 7.7. So if you wondered where it went to, you've done it. And now we're about to do 7.8 for what's left of today. So if you give me a few seconds, I'll get the intro to this setup. Okay. Well, I got a chart. So something I should know. That is a good comment. Ariana said, if we do that optional homework, will it give us extra credit? And yes, why not? I will give you, you're allowed to get 2% extra credit, and a lot of you haven't done the intro to Canvas, but if you do this one, I will give you 2% as extra credit. So it's still optional. You might say, I'm not going to spend 2 hours or whatever doing this. Yeah, why not? That seems fair. You're going to put in the extra work, you deserve something. So 2% extra credit for anybody who wants to do that. Now, let's return to the white screen. And I'm not even going to tell you yet what an improper fraction is, but we need some skill sets. We need to learn how to do limits. Now, you did them in Calc 1, and you might have thought that was the end of them, but it's not. And in particular, we're going to find out how to do limits as t tends to infinity of fractions. So let's just focus on how you find limits as t tends to infinity of a fraction. Almost every situation you're going to deal with will be a fraction, right? So it's special in that sense. Now, there are a number of techniques for finding limits as t tends to infinity. One technique is called brute force, which is my name for it. It doesn't have a real name that I know of, at least. And brute force is you just put in t equals infinity and you get an answer. Sometimes you do. The second technique involves you dividing the top and the bottom by a power of t. So you divide the top and bottom by t or t squared or square root of t or something, right? That's a second technique. And the third technique use a thing called L'Hopital, or as I call it, L'Hospital. Can you remember L'Hospital? Right. He says that if you want to find the limit as t tends to infinity of a fraction, so I'm going to call the top f of t and I'm going to call the bottom g of t, that you can find the limit as t tends to infinity of the derivative of the top and bottom. And this answer will be the same as that answer. So that's an example of one of these fractions as t tends to infinity. You can also do t tends to negative infinity, and it's the same basic techniques. So let me show you some brute force questions first. Four over t. If you plug in infinity, you get 4 over infinity. And think of infinity as a really, really big number. Won't 4 over infinity eventually get an answer that's so close to 0, you couldn't tell the difference? So 4 over t, if I was trying to find its limit, as t becomes infinitely large, its limit would be 0. How about t cubed plus 1 over 7? Well, if you plug infinity in here, don't you get infinity cubed plus 1 over 7? And then calculations with infinity are a little bit different than other calculations. Do you know infinity cubed plus 1, isn't it still just infinity? And what happens if you take infinity and you divide it by 7? Isn't the answer still infinitely large? So when we do some of these questions, actually pretty much all of these questions, you're going to get a number, might not be 0, in this case it is, or you're going to get infinity. So far, so good. Now, brute force really doesn't work in many situations. It does work now and again, right? I'm not saying it won't work in every situation. There will be questions where it works fine. But it's probably not going to work for the majority of the ones you're likely to see. So there's some examples of brute force. Let's show you the divide top and bottom situations. So suppose I wanted to find the limit of t tends to infinity of t cubed plus t over t 2t cubed plus t squared plus 5. Now, I can't do brute force. If I try to do brute force, wouldn't the top just be infinity? But won't the bottom also be infinity? And infinity on the top divided by infinity on the bottom, no, it's not 1. It could be anything. Yeah, you don't know the answer. It's called indeterminate form, is the jargon name for that. So in this case here, what I'm going to do, or what we should try and do, is divide the top and bottom by a power of t. And you decide by looking at the top. Would you agree t cube's the biggest power of t? And oh, it's t cubed in the bottom. So in this question, you divide the top and bottom by t cubed. And our question now becomes 1. T divided by t cubed gets you 1 over t squared. 2t cubed gets me 2. That guy gets me 1 over t. And that last guy gets me 5 over t cubed. Are you happy about what happened to each of these 5 terms when I divided them by t cubed? Now, once you do that, you essentially then use brute force. So let's see what happens. Isn't 1 over infinity squared 0? So you get 1 plus 0. 2 plus 1 over infinity, which is 0, plus 5 over infinity cubed, which is still 0. So you get 2, and your answer is a half.
We slide it up a little bit.
Yeah. You see how that one works? Now, let's do another one of these. Let's suppose I wanted to do the limit as t tends to infinity. And it's going to be 2t squared plus 1 and 4t cubed plus t. Now, we're still going to, whenever you see this situation, you're going to divide top and bottom by the same power of t. Right? You can't say I'll do the top one with t cubed and the bottom one with t squared. Algebraically, that's not going to work, right? So the biggest power is t squared on the top, and the biggest power of t is t cubed on the bottom. We have to choose one of those two. If they are not the same, pick the smaller one. So there's a t squared and a t cubed, pick the t squared. And let's see what that turns into. It turns into the limit as t tends to infinity. That guy is 2. That guy is 1 over t squared. This guy is 4t. And this guy is 1 over t. And once you've divided the top and bottom by t cubed or t squared or whatever it is you've decided, you then do the brute force. 2. What would 1 over infinity squared get me?
0.
0. What would 4 infinities get me? Because 4 times t is 4 times infinity. What would 4 infinities get me?
Infinity.
And wouldn't 1 over infinity get me another 0? Which means this is 2 over infinity. Now, this is a doable question. What would 2 over infinity give me as a limit?
0.
And so that answer would be 0. So that's the second technique. The second technique, you divide the top and bottom by powers of t. That is probably going to be the technique that you'll use most often out of the 3 techniques. So now we have one last technique called L'Hopital. You're going to use L'Hopital typically when your fraction has at least one term that is not a power of t. You know, so if you got a e to the t, I'll make that t squared plus 1, right? Let's do that, right? Something like that. That would be a candidate for L'Hopital. Sine 1 over t cubed, right? Things that just look weird. For what, I can't think of another way of saying it. If they don't look like normal fractions, right, with powers and t cubes and 3t squared, if they don't look like that, you're probably looking at a L'Hopital question. According to L'Hopital, he says that if you want to find that limit, you can find the limit of its derivatives. So you can find this answer instead. Well, if you differentiate e to the t, you get e to the t. And if you differentiate the bottom, you get 2t. Now, if I plug infinity in here, e to the infinity is infinity, and two lots of infinity are still infinity. I get that. Brute force doesn't play well with infinity over infinity, right? It's called an indeterminate form in that answer. But that's okay, because what L'Hopital says is, if it doesn't work, just do it again. So differentiate the top and differentiate the bottom. And now plug in infinity. Right, what's e to the infinity? What would e to the power of infinity get you?
Infinity.
Infinity. And would you agree infinity over 2 is just infinite? So your answer is infinite. Suppose we do it the other way around. Right? Pretty much the same fraction, but reciprocal. You differentiate the top and bottom. But that doesn't work. So you do it again. And now you can do brute force. And infinities can happen quite often. Zeros can happen, and halves can happen, and any other number that you can think of could happen. Are we good so far? Is that kind of helped you remember what you would have done in Calc 1, right? How you find limits of fractions in particular, and how you find limits as t tends to infinity of fractions. So now we're going to look at what are called indefinite integrals. Not indefinite, improper integrals, sorry. Funny name, improper integrals of type 2, but that's what they're called, so that's their name. And what do they look like? You're going to be asked to find the integral from 1 to infinity of some fraction. Like that. Now, that is not a typical integral, because normally you don't get integrals where one of the limits of integration is infinity. But in this case, that's exactly what you get. And we're going to be trying to find out, does this integral actually equal something? Now, side issue before we go back to this guy. If you put it into your calculator, this fella, well, we're only interested at 1. He'll probably look a pretty boring function. He'll probably look something like this. And we're trying to find that area. Now you might think, well, it's going to be infinite because this goes on to the right forever. And so there's always going to be some area there, and it'll add up and it'll keep adding up until, you know, you get infinite. But the answer is surprising. It's not always the case. It is possible for this fella, right, to actually equal a number. So your answers are going to be one of two things. You're either going to say, and this is the jargon that we use, that it converges to, I don't know, 4, right? Whatever the number happens to be. Or it diverges to infinity. And our quest in improper integrals, type 2 right now, is to find out which this is. Does it converge to a number like 4? And if it does, what is that magic number? Because it might be a half. I need to find it. Or does it diverge? And if it diverges, I don't care. Diverge is enough. You don't need to say anymore. Okay, if you got the goal in mind, what we're trying to do here. Now, I may not have convinced you that that could be finite, but trust me, it can, right? Analogy. Have you ever seen this? Maybe this will help. Can you imagine I keep adding those fractions up to eternity? Do you know that has a limit of 2? Yes, you're adding more and more terms, but aren't the terms getting smaller and smaller as well? Don't know if that helps, but it is true. So let's return to this question here. You want to find the integral of whatever the fraction happens to be. You will turn it into this fella. So I've removed the infinity and I've just made it a t, and then I've turned this thing into a limit. Can you see how we're going to be dealing with limits? So I need to figure out what this darn thing is in terms of t, and then make t go infinite and see what we get. I didn't give myself enough room, so I'm going to rewrite it over here. So you don't need to write this, I'm just repeating myself. Right, look at that ugly integral, right, this bit here. How do you integrate x squared over x cubed plus 1? X squared at the top, x cubed plus 1. How do you integrate it?
U sub.
Great. What will the u sub be? And don't overthink this one.
X cubed plus 1.
Agreed. You all comfortable with that u sub? Right. Differentiate with respect to x. Crossover. And then isolate. Now this is going to be the limit as t tends to infinity. Whenever you do a u sub, this 1 in the t should disappear until you get back to the x's. So I'm just going to call it that guy right now. And I've got an x squared over a u times 1 over 3x squared du. And what I've now got is cancel. I've got 1/3 1 over u du. And then I integrate, and I get 1/3 the natural log of u. Then I return back to my x's, and it's 1/3 the natural log of x cubed plus 1, evaluated at x equals 1 to x equals t. Do you see it's at this point here, once it's back into x's, that we bring the limits of integration back into the question. Now I'm treating t as if it was 42. It's just a term, it's just a fixed value. So it's 1/3 t cubed plus 1. Take away 1/3 the natural log of what? 1 cubed plus 1. And as weird as this question might look, it's not a fraction. So I have got a very good chance that brute force should work. So let's see what we get. 1/3 the natural log of infinity cubed plus 1. Take away 1/3 the natural log of 2. Okay, would you agree that infinity cubed is infinite? And infinity plus 1 is still infinite. So what have I got? 1/3 the natural log of infinity. Take away 1/3 natural log of 2. What's the natural log of an infinitely big number? Isn't it also infinite? You know, e infinity is infinite. You know, infinity cubed is infinite. So what do I get? 1/3 of infinity is infinity. You're really not going to do a lot of damage to infinity by subtracting that. So the answer is infinity. So we will say that this fella diverges. And that's all you put inside your box. If the area is infinitely large, it diverges. Okay. So let's show you another one where it converges to a number. How about the integral from 1 to infinity? Shall we do it this time?
So when we're doing these problems, we're just trying to figure out if it diverges or converges. We're not trying to exactly figure out the value.
Oh, we are. When it does converge, we're going to figure out the value as well.
Okay.
When it diverges, we just say diverges. But when it converges, it won't just be converges, it'll be converges to 2, converges to 40, converges to a half, right?
Okay.
That last bit, which this one is going to be an example of that, also is part of the puzzle. Right, would you agree that we turn this fella, this is step 1, into a very similar looking question, right? That's your first step. Now, don't make your life more difficult than it needs to be. Sometimes the simplest approach is the best. Would you agree that 1 over x cubed could just be called x to the -3 and I could use the power rule? Right? So, because sometimes what happens is you get caught up with some really difficult questions that you want to do really clever techniques on very simple questions that don't need them, right? When there's just a power rule, doesn't need it. So it's going to be the limit as t tends to infinity. If you add 1 to the power, you get that. And if you divide by the new power, you get that. And in this case, there's our limit integration. I'm going to do something which is basically what I call style points. It's always a good idea to turn your answer so it looks like the original, right? In this case, it's very important that you do that because I am now about to do brute force on this one. Whoops. Oh, yes, I have one more line, I was right. -1 over 2t squared, take away -1 over 2 times 1 squared. So that's going to be the limit as t tends to infinity of negative 1 over t squared plus a half. Now, we can use brute force on this, can't we? Great. And what do we get? I get negative 1 over 2 lots of infinity squared plus a half. Wait a minute, isn't that just infinity and 1 over infinity is 0? So I get 0 plus a half, and that's a half. So we would say that this fella converges to a half. You see, in this case, the answer also has what it converged to as a number, in this case, half. So when something diverges, you just say diverges. And when something converges, you typically are asked to find what it converges to. Are we looking, is this looking okay as a process? Good. A lot less work than what we did earlier today. Actually, for about the last week, haven't we been doing some really heavy duty algebra? Compared to what we've done, this is not that bad. I hope that's your feeling too. So, of course, I've just timed out, so that makes it a little bit harder for me to pick one of the homework questions. So I'll just pick one of my own. Let's do the integral from 2 to infinity of that guy. And this one is going to become the limit as t tends to infinity of the integral from 2 to t of x log x dx. Great. I hope by now that you realize how we convert this into this format, right? So let's work on this fella. Actually, change of plan. This guy here is going to take a lot of work. So rather than me writing down a whole load of limits as t tends to infinity in each line of working and thoroughly confusing myself, let's just find out what this is equal to. And once I know what this is equal to, can't I then plug it in here? Right, call it good. Right. T2 don't matter a darn thing. What technique will I use for this particular question?
Integration by parts.
Correct. Integration by parts. Now, when you do integration by parts, don't you have to pick an F and a G? I need an F and I need a G. Who are you picking?
I'd use natural log of x as f.
Do you recognize that question or something very similar to it when we did integration by parts? Right? I'm sure you've done a log x or an x squared log x or an x log x cubed, you know, those kind of guys. So, I mean, that's just experience, right? The more questions you get to do, the more comfortable you are with how to solve a question. Can you see in these questions, nobody tells you it's a U sub. Nobody tells you it's an integration by parts. Right? You need to be able to look at something and say, that's what I'm going to do. Now, the derivative of this guy is 1 over x, and the antiderivative of this guy is 1/2 x squared, right? And the fella that we're trying to do, which is this fella, is f of x, capital G of x, take away the integral of f dashed x, capital G of x, dx. And f of x is this fella, and the other guy is 1/2 x squared. The derivative is 1 over x times a half x squared. And that's natural log of x, whoops, 1/2 x squared, natural log of x, looks nicer that way. That cancels one of these and you're left with that. And this is 1/2 x squared natural log of x. This guy is 1/4 x squared. And the 2 to t belongs to everybody. I know the notation doesn't look like it does, but it does. It belongs to everybody. That term included. Now, if you plug this fella in, you get that. Take away, if you plug 2 in, well, 2 squared is 4. You get 2 log 2, take away 1/4. So I'm going to be looking at 1/2 t squared natural log of t, take away 1/4 t squared, and minus this bit. I didn't leave enough room, did I? Minus 2 log 2 plus 1/4. This expression here is a bit messy. Do you know what the answer is going to be when t goes infinite? I'm just doing a kind of brute force version. Well, let's break it apart. The number doesn't matter right now. If you pull out t squared, you essentially get that, right? I guess you get that, right? Okay, let's see what happens when t goes infinite. Would you agree this is infinity squared, it's infinity? Right, what would log of infinity get you?
Infinity.
Right, would you agree that taking 1/4 away from infinity is not going to do much damage? Don't you get infinity times infinity, which is infinity squared, which is infinity? Can I just put in infinity and say diverges? So essentially I use brute force. Right, brute force is just you replace the t by infinity and you make some reasonably obvious conclusions about the answer being infinite or not. Are you convinced that that would be infinitely large if you had to do it? Okay. For the 10 minutes that we've got left, I want to show you some weird ones. I would like to do the answer to this one. And I'm not going to do this using any integration techniques at all, although I guess I could try. Would you agree that that's what sine x looks like, at least if you go to 2 pi? And if you wanted to travel a little bit further, that would be where 4 pi is, right? If you kept on going to infinity, this fella here is divergent. And you might say, wait a minute, the answer is not infinitely large. That is correct. But divergent doesn't need to be infinitely large. Divergent's a catch-all phrase for the answer isn't a number. Now you might say, well, yeah, it's a number. If you stop here, won't the answer be 0? Because the bit above will cancel. And if you stop at 4 pi, won't the answer be 0? Agreed? But where's infinity? Infinity is not a multiple of pi, is it? Can you imagine you stopped here? Wouldn't the answer be slightly positive? Because that bit and then this bit here. If you stopped here, it'd be a little bit more positive. If you stopped here, it would be even more positive, and then it would get smaller and smaller, and back to zero eventually. So this particular one is divergent only because we can tell when we look at its curve that it doesn't become very small. Isn't that what functions have to do if they're going to converge? Now, how about this silly one? Do you recognize the integral of 1 over 1 plus x squared? It's a standard integral. Can you remember what it is? This is going to be the last one for today.
Inverse tangent.
Yeah. So what we're going to do is the limit as t tends to infinity of the inverse tangent evaluated at 0 and at t. And this is going to be the limit as t tends to infinity of the inverse tangent of t, take away the inverse tangent of 0. And that becomes the inverse tangent of infinity, take away, well, 0 actually, because inverse tangent of 0 is just 0. And the mistake that people make here is, because most of the time it's true, that if you want to find a function at infinity, it's probably going to be infinitely large. Or like the cosine of infinity, it's not got any predefined finishing value. But do you know the inverse tan of infinity is a number? If you sketch the inverse tan function, it looks something like this. And as this gets infinite, it levels off a particular value. Can anybody remember what that value would be?
Is it 90?
Yes, only we call it pi over 2. So that one there actually converges. And it converges to pi over 2. Whew, well, we did a lot today. So say hi, and I'll see you on Thursday, where we'll look at some more homework questions of type 2, and then we'll show you how to do what's called type 1. And that will be the end of improper integrals. Bye-bye, guys. I'll hang about if anybody has some questions that they want to ask. Hi, Matt, if you got a question. Matt, are you here? Because I can't see you. Nothing's moving. Okay, I'm going to assume that you locked out.